Okay, let's just jump right into this. For decades, the floor of the Indian Ocean has been hiding a massive structural paradox. In today's explainer, we're going to use the absolute latest seismic data, deep-sea drilling logs, and gravity models to finally crack this geological cold case. We're talking about unlocking the true origin of the Laccadive Ridge. I want you to picture something for a second. Imagine a massive underwater mountain chain stretching an unbelievable 2,500 kilometers across the ocean floor. Now ask yourself, how exactly do you build a colossal structure like that? Is it just millions of years of continuous volcanic eruptions piling up the salt? Or is there a much older continental foundation secretly hiding right beneath the surface? Well, that is the exact puzzle researchers have been wrestling with in the western Indian Ocean. Just to ground ourselves in the geography here, the Chagos Laccadive Ridge is this massive curved plateau sitting just off the western coast of India. Now, the northernmost segment of this, the Laccadive Ridge, actually runs right parallel to the coastline. And if you just look at a standard bathymetric map, a map of the ocean floor, it looks completely normal. It looks just like a continuous classic oceanic ridge. But as we're about to see, surface topography can be incredibly deceiving. So for decades, scientists were basically split into two camps, fiercely debating how this ridge formed. On one side, you had the Oceanic hotspot track theory. These folks argued the ridge was simply a trail of volcanoes left behind as the Indian tectonic plate rapidly moved north over a stationary deep mantle plume, the famous Réunion hotspot. But then, on the exact opposite side, a competing group proposed the Continental sliver theory. They argued, no, this is actually a sunken fragment of an ancient continent that tore away from India and Madagascar. So, which is it? A massive pile of oceanic basalt or a lost sunken continent? Well, our first big clues actually lie deep underground. You see, normal oceanic crust is usually only, say, 6 to 13 kilometers thick. But when we look at seismic profiles of the Laccadive Ridge, we see this incredibly thick 24-kilometer crust, and it's distinctly layered. The upper crystalline crust shows seismic velocities that perfectly match stretched continental basement. We're talking rocks like granite and gneiss. But right beneath that, there's a massive, extremely heavy magmatic lower crust that drops all the way down to 25 kilometers. So literally, we have continental rocks sitting directly on top of a massive igneous base. Now, from a mechanical standpoint, this ridge is a massive anomaly. Let's look at its effective elastic thickness, or TE. It sits at a shockingly weak 3 kilometers. To put that into perspective, ancient continental fragments usually have a really high TE because they're cold and rigid, and even fast-moving oceanic plates should be much stronger than this. A value of just 3 kilometers? That means the lithosphere here was highly, highly compromised. And that brings us to a really fascinating geodynamic puzzle. I mean, why is this lithosphere so incredibly weak? If this was just your standard oceanic crust forming on a fast-moving Indian plate, it absolutely shouldn't be this weak. So what exactly stretched and damaged this rock, kind of like thinned-out pizza dough, before the volcanism even started? The only way a plate gets this weak is if it goes through intense, prolonged stretching and rifting. So this tells us the Laccadive block experienced some major trauma long before any hotspot volcano ever erupted over it. But here is where we get the massive plot twist. Scientists actually did some deep-sea drilling at the Padwa Bank, right up in the northern part of the ridge. They drilled down through the tertiary sediments and finally hit basement rock. And guess what? Instead of pulling up normal oceanic basalt, they found acidic rhyolites. These are distinctly continental rocks. And by using high-precision argon-argon geochronology, they were finally able to pin down exactly when these continental rocks underwent melting. And this perfectly illustrates the paradox. The rocks they pulled from the Padwa Bank date back 76 to 78 million years. But the Réunion hotspot, that massive mantle plume that supposedly built this entire ridge, well, it didn't even arrive until about 65 or 66 million years ago. Do you see the problem here? You literally cannot have the trail of a hotspot form 10 million years before the hotspot actually gets there. That is impossible, and it completely shatters the idea that the Laccadive Ridge is just a simple oceanic hotspot track. So to really make sense of that dense lower crust we talked about earlier, we have to talk about something called magmatic underplating, because the Laccadive lithosphere was already stretched out and thinned to that super weak 3 kilometers. It just couldn't handle the thermal power of the Réunion hotspot when it finally did show up. So immense volumes of heavy, dense magma just ponded and cooled at the base of the Earth's crust, permanently thickening it from the bottom up. Okay, let's put this all together chronologically on a timeline, because a really amazing geodynamic story emerges here. First, around 88 million years ago, India separated from Madagascar, and this caused extreme stretching and rifting along India's western margin. Then, between 78 and 76 million years ago, that stretching actually caused the crust to melt, which created those Padwa Bank rhyolites and permanently weakened the plate. And finally, between 66 and 60 million years ago, the Réunion hotspot arrives. It punches through this thinned continental sliver and causes that massive magmatic underplating. So what does this all mean? The crucial takeaway here is that this ridge isn't an either-or situation at all. It's actually a brilliant synthesis of both theories. The Laccadive Ridge is literally a piece of the ancient Darwar Craton, part of a lost Precambrian microcontinent called Mauritius. First, it was structurally separated and permanently weakened by passive margin rifting. But then, millions of years later, it was heavily modified by the active Réunion Mantle plume, causing massive lower crustal underplating. And today, it's locally stabilized, totally supported by that deep, heavy magmatic root.
This beautifully summarizes our geodynamic mystery. As the quote lays out, it's a hybrid geologic feature. It proves that the ocean floor isn't just, simple oceanic basalt. It can be a highly complex hybrid geological marvel. Think about it. A fragmented piece of an ancient supercontinent was stretched thin, broken off, and then essentially glued completely back together with millions of cubic kilometers of mantle magma. Absolutely incredible.
As we wrap up this explainer, I want to leave you with a rather provocative thought. We just looked at how gravity, seismic waves, and argon isotopes revealed that the Laccadive Ridge is actually a fragmented piece of the ancient Mauritius microcontinent, heavily disguised by hotspot volcanoes. So, if a massive piece of a continent can hide in plain sight beneath a volcanic cap right off the coast of India, what other ancient, lost worlds are waiting to be discovered out there in the deep ocean? Definitely keep that in mind the next time you're looking at a map of the seafloor. Thanks so much for exploring this with me today, and as always, keep questioning what lies beneath the surface.